Hello everyone, my name is Fatima Nasiri and I'm going to present you our paper entitled Model Selection CNN-based VVC Quality Enhancement. Let's start with the introduction section. Video codecs aim at reducing the bitrate in order to decrease the traffic pressure on transmission network. The next generation video codecs, including versatile video coding or VVC, AV1 and AV2, and essential video coding or EVC are supposed to bring a significant improvement over existing video codecs like HEVC. Although the new video codecs are employing more advanced and complicated tools in their encoding process, the videos encoded with these codecs are still suffering from compression artifacts. Blurriness, blockiness, ringing artifacts are some of the well-known compression artifacts which are clearly visible in the videos encoded with these codecs, especially in low bitrate. So where exactly these compression artifacts are coming from? Here you see a simplified block diagram of VVC encoder. The block-based hybrid video coding, which has widely been using in recent video codecs, introduced some discontinuities in block boundaries and caused the blocking artifacts. The other source is the quantization. In lower bitrate, when we apply coarser quantization step to the transform coefficients of the residual signal, it may introduce some ringing artifacts or smooth the edges or see some blurriness in the decoded videos. So what are the current solutions to this problem? To solve this problem, we can employ some quality enhancement module during encoding and decoding process. These quality enhancement modules can be employed during encoding as in-loop filters. Here, because it's an in-loop process, the purpose is to reduce the bit rate and also improve the perceived quality. Once again, because it's an in-loop process, when it is used at the encoder side, it is mandatory to be used at the decoder side too. The other option is to employ this quality enhancement module after decoding as post-processing. Here, because we have already received the video, the purpose is to improve the perceived quality. But the advantages is that it can be optional and be used based on the hardware capacity of the user and the display that it's using. And now in VVC, we are using 4 in-loop filters. Here you see a simplified block diagram of VVC decoder emphasizing the in-loop filters. First of them is the blocking filter, which is for reducing the blocking artifacts. This filter applies some low-pass filtering in block boundaries to smooth the edges. The next one is SAO, sample adaptive offset, which is for reducing the ringing artifacts and correcting the local average intensity changes. This filter classifies the reconstructed pixel into some categories and then signals some information to the decoder. The next one, ALF, adaptive loop filter, is for further correcting the signal based on linear filtering and also adaptive clipping. The last one, luma mapping and chroma residue scaling, and it's not exactly for removing the artifacts, is for better using the signal range in order to improve the coding efficiency. Besides these handcrafted in-loop filters, recently there have been many studies proposing quality enhancement as post-processing and in-loop filtering based on a convolutional neural network. These methods provide a significant improvement in terms of bitrate saving and also perceived quality. So with this introduction, now I'm going to explain you our contribution, which is a model selection CNN-based VVC quality enhancement. Here you see the overall framework of our method. We are proposing a CNN-based post-processing for quality enhancement. The key element of our method is the use of coding information. The motivation behind using coding information is that if artifacts are caused by encoding tools, then why not let CNN know about them? The first question one might ask is that what kind of coding information can be beneficial here? Of course, quantization parameter or QP, which determines the level of distortion during encoding, can be beneficial. Partitioning can provide good information about the block boundaries. And finally, intra-prediction and intermotion compensation can provide a good information about the texture and temporal complexity of the video. So in our quality enhancement methods, we train different models for intra-coded frames and intercoded frames. In intra-coded frames, we extracted the prediction information, quantization parameter, and decoded videos, and fed our CNN network with these inputs, and we train this network to generate the most similar output to the original frame, the uncompressed one, by optimizing its parameter based on the given loss function. So why prediction information of intercoded frames can be beneficial here? Here there is an example of two reconstructed blocks coming from two different predictions. You can also see here the rate distortion cost, which is very close to each other. The value is very close to each other, but as you can see, the reconstructed block has a totally different type of artifacts because they're coming from two different predictions. So we decided to feed the prediction information to the CNN network to improve the performance and remove the artifacts more effectively. Likewise, in intercoded frame, we extracted the motion compensation signal, quantization parameter, and the decoded frames, and we fed them to our CNN network, and we train it in the same way that we trained our intercoded frame. Here, the reason that why motion compensation can be beneficial is that this signal, the motion compensation signal, is composed of different parts of a reference frame, which are normally encoded with lower QP, which have higher PSNR, which if you provide this information to the CNN network, CNN network can have access to some similar texture with higher quality. So it may improve the quality and remove the artifacts more effectively. In intercoded frames, we have different coding types than intercoded. So we have intra coding type and also the skip mode where the residual data is 0. So we observed in our experiments that these blocks are not properly enhanced by the dedicated network, which is trained for intercoded frame. So to overcome this problem, we trained the 4 different models for intracoded frame, 2 for intracoded frames, and 2 for intercoded frames. First of them was for intercoded frame, which we fed the network with reconstructed frames and also the quantization parameter map. The second model was fed by reconstruction signal, prediction information, and also the quantization parameter map. The third one, which was for intercoded frame, received as input the reconstruction frames and also the quantization parameter. And the last one received as input the reconstruction frame, motion compensation, and also the quantization parameter. At the encoder side, we divided each frame to non-overlapping blocks and then enhanced each block with these 4 models. Then we chose the best model based on the mean square error, MSE, and then we signaled the index of the best model to the encoder. At the encoder side, the models are available. So decoder, so after decoding the video, by having the index of the best model, we enhance the quality of each method by its best model selected at the encoder. So let's see what are the results of using this quality enhancement method after decoding the videos. For network architecture, we didn't invest a lot of time. For feature extraction, we used some residual units. We used a 16 residual unit with global skip connection. Then we add some more convolutional layer at the end to construct the enhanced frame. For training dataset, we use BVI DVC, which is composed of 800 videos in different resolution, which was a great dataset for this application. For training the intercoded frames, we also use two image dataset, diff2k and flickr2k. We performed our training with the dataset encoded with PTM10 in random access configuration, 10-bit in 4 QPs. We also extracted the reconstructed frames, prediction, and the quantization parameter map from each decoded videos. As loss function, we used the L1 norm. During encoding, we extracted the 64 by 64 patches in batch size of 32. For training, we use the PyTorch, and for inference, we use the libtorch in C++. So here is the result table of our proposed method, showing the results in 3 columns. In terms of bitrate saving, the anchor is VTM10 in random access configuration. First column of the result shows the setting that we have trained our network without any prediction information. And as you can see, in average, we have obtained 5.79% gain. When we add the prediction information to the network, we get 7.16%. And moreover, when we add also the model selection strategy to the prediction awareness, we get 7.62% gain in total, in average. Here also, there is a rate distortion curve of one sample from class C that shows that we have a consistent gain all over the bitrate range. And also in this slide, you see our results, which are compared with some state-of-the-art methods. And here you see that our method is outperforming all these methods. It is worth mentioning that, as you can see, our baseline, the prediction on error setting is worse than the MFRNet method, which is employing a very efficient architecture to their quality enhancement. So we can conclude that if we add the prediction information and also the motion selection strategy to MFRNet, we can also get higher gain in terms of bitrate saving, which is left as a future work. So to wrap up this presentation, you observe that the CNN-based quality enhancement methods are competing with handcrafted standard methods like DBF, ALF, and SAO. And you also saw that use of coding information can help CNN learn the artifacts pattern more effectively. In our quality enhancement method, we use the prediction information of intracoded frame and motion compensation signal from intercoded frames, and also the quantization parameter. We also adopt a model selection strategy, and you observe that our method is outperforming most of the existing quality enhancement methods. Thank you. I will be here to answer your questions.